Okay, so now we're going to cover dampers. So, unlike masses, which store kinetic energy, and springs, which store potential energy, dampers only waste energy. Therefore, they don't store energy at all. They tend to relate to inefficiencies in a system. That doesn't mean that they're always bad. Sometimes we need dampers in our system, but they are related to inefficiencies. So, for an example for a damper, we can think of a cylinder with a fluid in it and a piston. As we move the piston, the fluid makes it more difficult than if there was no fluid at all. It acts effectively like friction, so you need more energy to move that piston. So let's draw that out as we can see here. And if we were to move this our cylinder downward, the fluid would go through those little holes in our cylinder and essentially create a resistive effect in this case. And something like this is used in a door closer with air as that working fluid. It's necessary, we need this damper in here, or else the door will just open or especially close too quickly. And another example of a damper that we would need is a shock absorber, like those near car and plane wheels. So the big thing with dampers is that a damper resists motion. It does not need to be related to a fluid. It can represent things like friction. An ideal, as in no mass linear damper, is described by an equation similar to Hooke's law. However, dampers resist motion, so damping force relates to velocity. So if we have our damping force, which is equal to our damping coefficient c times our relative velocity v, that is our damper's equation, damping force equation. And we usually draw a damper with the symbol that looks like this. It's essentially a little dash spot, the same case that I showed in the last slide. So unlike masses and springs, which have mv dot is equal to something and d dot is equal to something, dampers do not, as they cannot store energy. So they're just a static relationship as we see here. And that's going to cover dampers.